So I'm very pleased to introduce Agustin del Prado from BC3, which is the Basque Climate Change Centre for Climate Change. Yeah, it's BC3. And I was just adding it up. I first met Agus 10 years ago, which I found a bit scary, when he was working for Northwick, and we started working together on a DEFRA project. We're both modellers, and actually we do model similar things, but I like to think we're complementary rather than rivals. And I'm sure Agus will tell you a bit more about his models, but focusing on the dairy sector, but also modelling many other things. So you're now a professor at the Basque Climate Change Centre, and also a lead author on the forthcoming greenhouse gas inventory, IPCC greenhouse gas inventory, which I think there can be big changes in that? Or?
Some changes.
Big changes in that.
Yeah, I'm officially not allowed to say them.
Okay, sorry. Okay.
Big changes.
So, but today you're going to talk to us about sustainable intensification and your sort of thoughts and approaches to it. And yeah, that's really good. So I'm really happy to introduce Agus and really look forward to his talk.
All right, thank you very much. I'm going to time myself so I can be slow enough so I can beat myself in a way I finish this on time. Okay. First, I would like to thank whoever was involved in deciding that wanted to invite me over. I really want to thank you because I've heard a lot about Bangor, especially from some colleagues that I've worked in the past with them. I still collaborate, and it's really a great pleasure for me to be here. So just one spoiler before I start is that this is this lecture about sustainable intensification, but I mean, rather than giving you already solutions about this potential issue of sustainable intensification altogether, I'm going to probably provide more questions really than answers. So okay, sustainable intensification is a term that was coined already back in 1990 in the context of agricultural smallholders in developing countries that had low productivity and already quite a lot of concerns to do with land resources. Well, at the beginning, this term was sustainable intensification. The emphasis was placed equally, the emphasis. But now it's rather than that, it's taken more as a global and mainstream agricultural concept. So it's more for a global framework and not so much for developing countries. So why do we need this sustainable intensification? What are some of the reasons? So first one is the idea that we need more food to feed this growing and richer population. So we already have seen through the global statistics that the richer the countries they get, the more calories and proteins per capita they generally consume, and this also has the same really effect on the amount of animal proteins, on the share of the animal proteins and calories that their diets will be also consuming. Obviously, it would be naive to think that this is the only problem, so the problem of food availability. There are other problems that have to do with how the food is distributed around the world. So it's not just about the food productivity, but well, obviously this is certainly one of the main concepts to have in mind. Another one is that the arable land base cannot be expanded. This is a global map with the proportion for different countries of arable land or over the total land they have. So it's different it varies from different countries. And the third concept of why we need this sustainable intensification is that, apart from being more sustainable, our agriculture needs to be more efficient in terms of resource use. So one thing that could come into our mind and what is actually happening is that can we be more efficient in our production through having farms with more productive animals? So I wanted to use the nutrients and the nitrogen in this sense at the farm scale. To give us an example, if we improve the nitrogen use efficiency at the farm level, can we actually see that is more sustainable or less sustainable. So what I'm going to actually show is, well, this is a typical dairy farm with the 4 main components. One is the animal, the ruminant. Another one is the plant that goes to the animal, that's for feed. There is a component of excreta, dung, urine, manure. It depends whether they are housed or grazed. And there is a component that has to do with the soil. So the main inputs to the whole farm would be through feed that can be bought into the farm. So that could be using some nitrogen somewhere else, both in terms of nitrogen fertilization, or if they use legumes somewhere else to produce these concentrates, that would use nitrogen through N fixation, atmospheric fixation. There could be nitrogen fixation as well directly in the farm if we have legumes growing. Through the soil, we can have more fertility in the soil to grow more plants through applying more mineral fertilizer, more synthetic fertilizer, and we have an unavoided flow of nitrogen that comes from the atmospheric deposition. That's also important. And at the manure level, especially at the housing level, we may have some inputs of nitrogen in terms of bedding, like for the cattle. So some of the output, useful outputs, milk and meat, obviously. Then we can have some of the forages that can be sold, or even sometimes you can export some of your manure from the farm. But then you have other unavoidable nitrogen losses that you are not so interested in, which are the ammonia losses that are coming from the manure management, or the nitrous oxide, N2O, which is a potent greenhouse gas emission. And from the soil perspective, you may also have ammonia and N2O as well, nitrous oxide. You may also have NOx, nitric oxide, or you may also have nitrogen that is going to the water through leaching or runoff. And you have other nitrogen that is also part of the economy of your nitrogen use, which is the nitrogen gas, which is not a problem for the environment, but it's rather a loss. It's also a loss for the economy of the nitrogen in the nitrogen use. So there is also some losses that may happen at the silage making, at the silage process in terms of ammonia or NOx. So what I'm going to try to do is present some results as an example that we did like 10 years ago using this model, which is called SimsDairy, that we developed back in the 2006. And from 2006, that was through a project from DEFRA, and involved several institutes, apart from what is now Rothamsted, which was at Northwick Eiger at that point. So some people here are actually co-developer of this model. So there are other centers that were also connected to produce this model. So this farm model allows us to simulate the effect of the farm management and the interactions with the genetics of the animal or the plant, also together with the climatic conditions and the soil conditions in the area that we are trying to simulate, over the nitrogen and phosphorus flows, transformations and losses, greenhouse gas losses like from carbon, like methane. We also can simulate the animal performance and the requirements. There is an interaction with the farm economics by having a whole farm economic balance. And it was quite novel at that point, because it integrated as well other aspects of sustainability, which were to do with milk quality, for example, biodiversity, animal welfare, or landscape aesthetics. So some of the other attributes of the model capabilities was that it could optimize fertilizer management. It had a monthly time step, so it would calculate every month what was happening in the farm. It could incorporate as a crop, apart from grass and clover, it could incorporate other crops like maize, and now it can incorporate rapeseed as well. It would include some pre-farm gate emissions at this point, so those that have to do with concentrates or fertilizer manufacturing. And the newer versions are capable of simulating climate change scenarios, as well as different manure treatments or the effect of heat stress on the animal production and emissions. So by presenting what the tool I use for this example, so this is a theoretical example, like I said 10 years ago, that we simulated. So the idea was comparing the potential of making genetic changes either at the plant or at the animal basis, at the animal level, in a single trait of the animal or the plant, what would be the effect at the whole farm level in all of the emissions and productivity, etc. So, in one scenario, we increased the nitrogen use efficiency, so we kept constant the feed that we were giving to the animal, but we just increased the trait of the animal to produce more nitrogen, more proteins from this feed. So what it was expected, it would increase productivity. It would decrease as well, because we were using the same amount of feed, it would decrease the excretion, the nitrogen in the excretion, and that would carry over to the emissions that were connected to the excretion as well, that mainly ammonia and nitrous oxide, and also in the soil, because there were less nitrogen coming to the soil, there were as well less emissions happening at the soil level by making this change in the animal. So if we compare that to changing the ability of the plant to take up nitrogen from the soil, so we increased this as a trait improvement in the plant. This is all theoretically, obviously, so it's not we didn't test this in real terms. So by doing so, obviously the plant would increase the plant productivity, and that would also have an impact on the returns of the plant from the dead plant material and the roots and stubbles that would be incorporated in the soil. I would actually would feedback on some of the fertility of the soil for the plant as well. It would make increase because there would be more feed and more nitrogen in the feed. It would increase the productivity, but in this case, this would also increase the excretion because more protein would be going into the feed, and more excretion as well would be produced by the animal, which would have a negative impact on the emissions that were connected with the manure management, especially ammonia and N2O. But again, once you go back to the soil, because the plant was so good at taking up some of the nitrogen, organic nitrogen that was flowing around, this would make N2O and nitrogen leaching being much lower than in this baseline scenario where you didn't have genetic changes in the plant. So this is just to illustrate how changes at one point of the farm at one level may have a different implication at the whole farm level, and obviously if you would pass this to a greater regional level, you will have other implications. So it's important that we take that into account, as some of the strategies are sometimes extrapolated from the animal or plant level to greater levels without making this type of analysis. So from the theory, I'm going to try to be a little bit more practical, and I was trying to be a little bit more interesting than for you. That I thought that let's talk a little bit about Spain, and taking into account the weather conditions that we have. You might actually be interested in our context now, because you might be in the future a little bit like this anyway. So just this is interesting for you. So I'm going to use the whole dairy sector in Spain, not just the cattle, even though I'm going to talk a lot about cattle. But I think it's interesting in Spain because we have over 10% of our milk production comes from a species that are not cattle. So we have like almost 6% from sheep and 5.4% from goats. So actually in the EU 28, we are quite a big champions for sheep milk. We are first producer in Europe with a total amount of 17% over the total EU 28. And for goat milk, we are 22% over the total European, and we are the second producer of milk. So it is important sector in Spain. Significant milk is produced. Again, I'm coming back now again to where I know more is the cattle. So this is the evolution of median productivity of a dairy cow in Spain. So this is data coming from 1990 to that now, and the productivity has more than doubled. So it's come from 3,500 to around 8,000. This variability that I'm showing here is just the variability that we have in within the provinces, that the different provinces that we have in Spain. So I will show you later on that obviously we have different production systems, and they are very much related to the site conditions as well. So these are kind of the changes that it has happened, and so like I said, higher yielding cows are now the norm. So the main dairy cattle production is actually happened in the north, and in this particular area, which if you have France would be here, and this is the area, the Atlantic area, so the area that we have more pastures. So most of the milk production, dairy cattle production is concentrated there. So some of the statistics as well, apart from productivity, that this intensification or higher yielding cattle has brought with this. So we have some of them are quite expected. So we are talking about replacement rates that are being larger. So that's something that we would expect. The number of lactations per lifetime of a cow, of a dairy cow, an average lactation numbers have been reduced quite a lot. And another feature that has happened is that the lactations, the days of a typical lactation has been expanded. So we have longer lactations, fewer lactations, the longevity is also smaller, even though I don't have the numbers there. And also the drying period has also been shortened. So it's what we expected. We are trying to push harder the system, so we are trying to push the animals a little bit harder to get more production out of them. So I try to explain to make an effort, because this is not really something that is being published, so it's not a lot of work done on typologies in Spain as much as is being done here. So the type of the typical dairy farms that we would have in Spain. So I've done my effort, and a small effort, because I just didn't take the numbers are not exact, so it's just expert opinion. So we could have 3 typical systems which are associated to 3 different areas. So the first one is in this northwest area of Spain. This is the area with more farms, called Galicia, and this is the area where we still could find some farms that there is some grazing activity with dairy farms. So it's about it's less than 5% of the whole amount of farms in Spain. So they have the lower productivity of all of the systems, and they are, like I said, this is the Atlantic region. So this is it's a rainy area. So another of the majority of the farms are placed in the other region of the Atlantic region. So already also including this northwest, but also going more to the east. And the difference is that they use higher yielding cattle, and we have given up on grazing. So we still have the land, but we thought that this is much easier having higher yielding cattle and still having our land, which sometimes is challenging because it's not the main problem as well is that we don't have the plots concentrated in one area, but they are like dispersed, so that makes it difficult for the farmer really to manage like the grazing activity. So it's not that they don't like the grazing per se, but it's very difficult sometimes if you have this type of farms. Okay, and the third one, which is the rest of Spain, so it would be the Mediterranean area, or sometimes it's a little bit more continental than Mediterranean, but still, it's not rainy. It's not so rainy than the other rest. It's not the areas that you would find a lot of dairy cattle, but there is also always been some dairy cattle. And here we have this typically fully housed, and they don't generally have a lot of land. I said they don't have land. Obviously, there will be some that have land, but I have made this assumption, this simplification. So they are more like a pig farm, really, but with dairy cattle, bigger animals. And okay, they are very highly productive animals. And this is about 45% of the farms, I would say. And okay, so I could say that in terms of replacement rate as well, there is a gradient from lower to higher, depending on the yielding of the cows as well, as expected. And the amount of their diet that comes from concentrates as well as expected. You would expect that there's no more than 30% in the grazing in the farms that have some grazing, but for the rest it goes up to 50% in the one that is housed but still with land, and over 50% in the Mediterranean farms that will come from concentrates. So if we think about an intensification pathway, we would tend to think that what is happening already, and it's been happening in the last decades, is that this type of farm that has some grazing is really going to disappear and is going to be transformed to this other farm that still has land but has no grazing, and opts to have higher yielding cattle, so management that would evolve for that. So that would be kind of the scenario that I can give you as an example. Okay, so we are getting rid of the grazing for these dairy cattle. So if we assume that we have the same adult numbers that we used to have with the grazing typology, we would have that about, we would be producing with this intensification about 3% more milk, okay, or for Spain. And getting inspired from some paper from here, from Bangor, from David and James. Well, I'm using the same kind of table, a little bit more simplified as well. But what is the implications that you have with this intensification? So you have more concentrates requirements. You also have a tendency to get more forage maize, so you need some more forage maize for these systems that have been converted, and you need probably less forage, less grass from grass forage. So for the region, this has implications. For the concentrates, we assume that these concentrates mostly don't come from the area, so there's nothing really happening for the land use there. But for the land use in the region, so like I said, there must be some grasslands are converted into forage maize, and some of the forage, so there is a decrease in forage grass hectares and an increase in forage maize. So obviously, this will probably bring higher yieldings for these forages. So probably with these higher yieldings, because there are greater inputs to the system, this you could have either, if you keep the same amount of animals, you could have some land sparing, like some of the scenarios that here in Bangor they were simulating for the UK, or you could actually bring in more cattle. In this case, I was simplifying. I wasn't thinking about the beef in this case, so I was just thinking bring some more dairy cattle into the system, so you would have some more milk that would be produced in the area. And what would happen with the rest of the world? Again, like you could expect, because you need more concentrate, you need more hectares somewhere else. And well, for the forage maize and grains, we assume that we don't change the land use because it comes from the region anyway. Anyway, what are the implications of these changes? So first I'm going to think about greenhouse gas emissions. So it's one thing of the whole sustainability concept. It's just one thing, but an important thing. So if we think about how it's been evolving, the carbon footprint of milk production, well, it's a typical thing that you get in the US, that carbon footprint has been really reduced quite a lot, mainly because of this higher yielding cattle, much better feed, so that reduces the methane emissions. And also there's been a lot of changes to do with the manure management, which has made more efficient that part of the system, and has been creating opportunities to reduce the emissions at that stage. What happens at the national inventories level? And I've chosen the Spanish national inventory, and I hid the numbers because this is not published, so I didn't want to get into troubles. So, but you will see the tendencies. I mean, it's not really a big, but they could, bring me problems. So, if we think about the dotted lines are the absolute numbers, but the non-dotted lines are the relative, so the intensity emissions in this sense. So the emissions per liter of milk in this case. So the trend is that for methane emissions, there has been a reduction in intensity. So, well, okay, like expected, you're bringing higher yielding cattle, so emission intensity reduced. Volatile solids as well reduced per liter of milk, and this will be actually something that you will be used to derive methane emissions from manure management. So if there is a reduction in volatile solids, there will be also a reduction in methane emissions per milk production. And the same could be expected for excretion, nitrogen excretion, which would be the basis to derive later on the nitrous oxide and ammonia emissions from manure management or grazing or activities. But really, we think about the whole production system, life cycle analysis, and this is a graph plotting. Every dot is one study in the world, like relating cow productivity with the carbon footprint. So it's true that at the beginning of, with very low production systems with low production cattle, there is a sharp decrease in carbon footprint. However, it's not, yeah. If we look at the range that we are operating in developed regions, which is from 4,000, I would say, well, there's not such an evidence of the carbon footprint really being reduced by having higher yielding cattle. And I guess because this is global, I chose to also to add my own study from the Basque Country, and again, it's really the same kind of thing. It's not really a strong evidence that is connected the productivity of the cattle and the carbon footprint. So if we look closer to the different sources of greenhouse gas emissions, and this is coming as well from a summary of different studies that have been doing life cycle analysis, and this is not just for dairy cattle, but we are also thinking about beef and sheep, this meat sheep. And the two main sources are generally, or two of the three. Well, enteric methane is one of them for ruminants, for any product that involves ruminants. Another one is soil nitrous oxide. Then you could have as well methane and N2O coming from manure management. So it will depend on the share of this type of emissions for every species. So that will tell you as well how's the production system, if it has some more housing, less housing, if it has also when we talk about secondary emissions, we are talking about the emissions that are coming from outside of the farm in terms of concentrates, production or fertilizer manufacturing. When we're talking about, we're also talking about energy used in the farm. So if we think about the two main ones, so I think the two main ones, we can provide some examples. So how to calculate enteric methane, how to estimate enteric methane fermentation and soil N2O. And for the enteric methane, this first illustration, I'm using other species to draw a little bit your attention as well. This is a drawing from my daughter, so just keep with me. It's a nice drawing. We use for a PhD thesis as well. So methane is part of the energy balance of any animal. So the way it's estimated, this methane output is generally through calorimetric trials that they study the energy balances. So they have an assessment of how much energy the animals eat. They are using gross energy as the value. So in this case, some of this gross energy will be going to body retention or milk production. So I forgot to mention this is, I'm going to give some ranges, typical ranges that came out through a meta-analysis that we've done for this report that will come out in 2019 for the new guidelines of refinement of the guidelines for estimating greenhouse gas emissions from agricultural and livestock production. So importantly, feces has quite a lot of losses from this energy that the animal is taking in, but there's quite a lot of range we found in these trials. Urine has also important losses, and methane, well, it's quite varied. So it's we found that from 1 to a little bit more than 10% of the energy that these animals are eating will go to methane. So we try to relate this kind of information, again, this information from over 60 trials internationally, doing in calorimetric controlled conditions. And we were trying to see if this effect for the what I shown before, which was for the total carbon footprint, this is showing similar things, but only for methane. Okay, so for methane, you see some effect here at the beginning of the productivity, but then this high yielding goals really mask the whole statistic. So that was really bad because we were not able really to come up with some statistical result from that. Okay, so in terms of when we try to do carbon footprinting, or we use for inventories or for our farm models, if they are simple enough, we may use simple methods like the IPCC one. So the IPCC one, like from 2006, what it's trying to do is first estimate the gross energy intake of the animal as a function of the activity, of the breed, or obviously of the productivity, and then the age, and then from this energy, which will depend as well from the quality of the feed, it has a fixed factor, this widening factor, that is saying that for cattle. So I'm changing now. Forget about goats. I'm using cattle as well for an example. For cattle, will be 6.5% in general of the energy that the animal eats would come out as methane. However, there are some more recent methodologies that add another complication or another idea about this, and it's trying to have a non-cost constant factor, widening factor, which would be depending. So this percentage, 6.5%, of methane that goes out from the energy intake of the diet. Some people have come up with statistically with the factors that depend are a function of the quality of the feed. In this case, a function of the digestibility of the feed. So the more digestible the feed is, they came out with some new factors that it would show that the lower the proportion of the energy intake, gross energy intake, would go to methane. There is also another complication when you do this type of analysis, and it's the assumptions that you can have when you try to compare high yielding or lower yielding cattle, so a pathway of intensification. You may be, obviously for high yielding, you will be always assuming that they have very good quality diet, so that will be reflected in this digestibility, so high digestibility diets. But for low yield, you always, I want to show you what's as an assumption, what if you change like 5% is digestibility? So you may be thinking it's a very poor quality diet, but I mean, this is really a huge assumption what digestibility you use in your scenario. So I'm showing you what is the difference of using, for example, a 5% different percentage of digestibility, which still is not a good quality feed, by what we call more a moderate quality. What would be the outcome of your estimation? So we are thinking about different yielding cattle. We also will have a potential effect on the fat content of the milk. So when you do these comparisons as a carbon footprinting, you would be using as a reference not just a liter of milk, but you would be relating as well to a liter of milk that is corrected with fat, or only with fat, or also with fat and protein. So one thing that we need to take into account as well is that the higher the yielding the cattle as well, the lower the concentration in protein and fat they will have generally in their milk. Anyway, this is more of a side idea. So if we think that the intensification is going from, for example, from 15 kilograms milk per day to 25, so an increase of 10 liters of milk per day kilos. And we're using these two different approaches. So the approach of the fixed factor of 6.5 would result in this term on a 16% reduction of methane from going to 15 to 25. But if you use the other one, the one that is where the widened factor, the factor for the methane, is depending on the digestibility, you would get an even greater reduction. So in this sense, if you use one method or the other, you would get a very different value. And well, this converted to CO2 equivalents would make a big difference, really, when you are comparing systems and when you aggregate it with the different emissions. And then, if we compare the assumption I was saying before that we choose to have as an assumption a better or worse quality of the feed for the lower yielding cows, and we use the same approach as before, for the fixed factor, we would have a much lower reduction if we have a slightly better feed quality. And the same would happen for the other type of approach. So this would be a massive difference from 8% reduction of passing from 15 to 25 kilograms of milk per day to the other assumptions that we were having 17 or 34 reduction. So you could make a lot of well, different results by choosing one method or one assumption that both methods could be you could support. You could have grounds to use them, and the same with the assumption, and the results are very different. So we have seen so far that animals systems with lower quality feed, let's say, or that sometimes we have lower quality like those grazing or those very much focused on a lot focused more on forage, would have greater potential for methane and enteric emissions. But what about soil organic sequestration? Can we say anything about this? So one thing that we did recently was, we did a study of carbon footprint in 17 dairy farms in the Basque Country. So I've already probably mentioned that before. If I haven't, I will mention that later on as well in other examples. So we plotted the methane emissions per liter of corrected milk, per liter of corrected milk from the different farms, 17 farms, and we plotted that against an estimation of the soil organic carbon that we would have expected if we were thinking that these farms have been changing the production systems recently. And we found that there was a trade-off, obviously, that those that were using, that were having greater emissions from enteric fermentation had larger possibilities of soil organic carbon sequestration. So basically, those that were having lower amount of concentrates, worse feed, were associated to greater methane emissions, enteric methane emissions, but had associated as well some more potential for soil organic carbon sequestration. Obviously, that wouldn't offset. It's not like you would offset the emissions from this soil organic carbon. Now, plus, it's quite uncertain, this soil organic carbon estimation. But it's just to show that there is some certain. We could expect some certain trade-offs there between methane emissions from enteric fermentation and soil organic carbon in some situations. The same when we think of intensifying. So we are making a change of systems that we are introducing more nitrogen in the films per hectare and more carbon as well per hectare. So we are thinking of a change. So for some years, we may expect as well that this intensification would actually result in some soil organic carbon sequestration. And by using some estimates from some study, I mean, this you can have this is just a particular study that was relating, depending on the amount of slurry carbon inputs, there would be a different possibility of carbon sequestration per hectare per year. This would happen, again, like I mentioned before, this would happen for some years, if it's happening, until it gets to some kind of stable situation. But again, this should be taken into account, I think. So, soil N2O, okay. That's another part of the nitrogen cycle. So, another example. So, again, back to the whole diagram with all the flows of nitrogen in the whole farm, different components, and we're looking at the soil N2O. It's down here, and represents very small amount. This is an example taken. These are values taken from our study. It might vary, but we have that from 0.1 to 1% of the nitrogen inputs to the farm would be lost as N2O emissions. Okay. So in our scenario, remember, we are still coming back to this scenario of converting this situation of house and grazing systems with more fully housed, still with land in the northern area in Spain. We were thinking that we would be increasing these nitrogen inputs. Like we said before, we would be increasing carbon inputs per hectare. We could probably increase these nitrogen inputs per hectare. So what would that be the effect on the nitrous oxide on the soil N2O compared to the previous type of typologies? And here it's where, when it comes to the idea of using assumptions or methodologies. So the well-established methodology from the IPCC 2006 establishes that for most of the flows of the nitrogen inputs to the soil, the estimate is that you should use by default like 1% is lost at the field level of all of these inputs as N2O emissions. However, these are very recent meta-analysis. This is, for example, for cropping systems in Spain, and it's showing in this meta-analysis that this 1% can be challenged quite a lot. And moreover, it's interesting that for like when we think about cropping and we think that the irrigated systems are more intensified than rain-fed systems. So we have that for irrigated systems, the emission factors are much larger than for rain-fed crops. So again, like using this 1% for all of the systems, either they are intensified or non-intensified, like either they are irrigated or non-irrigated, we may be doing quite a lot of error, or at least it would be nice to refine this, at least now that we have more solid information. I mean, I know that this is going to be incorporated, some of it will be incorporated anyway in the refinement of 2019 of the IPCC, but you know, already we can already think about these things. Another global meta-analysis for grazing, and it's much lower as well than 1%. This is for cattle down urine and for sheep down and urine. Okay, so it's lower than 1%. Okay, there is someone here as well that has produced some information that is relevant for the UK, and that's for grazing situations 0.49%. Okay, I suppose it will be incorporated soon or already in the inventories. So, and that could be also incorporated in the life cycle analysis. Another issue, okay, when we intensify, we are increasing the rate, okay, of nitrogen inputs per hectare. So we are always assuming fixed factors that are irrespective of the nitrogen rate, but some studies have actually shown, and make sense really conceptually, that this shouldn't be linear, or there is the potential that this is not linear, and that the more you increase the nitrogen inputs, the more possibilities you have that the rate of N2O really increases exponentially. And these are two examples, one from the UK, okay, from 2010, grasslands, but this as well from completely different area, but also this is grazing from Kenya, so it's not just a temperate area that this has been found, this type of effect. So this conceptually makes sense because, I mean, once you increase the nitrogen inputs to the soil, the plant will have lower and lower ability to uptake proportionally the nitrogen from the soil, so it will be less efficient. So there will be more nitrogen in the soil left proportionally that could be either lost by N2O, N2, could be lost by nitrogen runoff, or could be actually, if it's too dry, it could be actually carried over for the following years, depending on the system. But this conceptually should be thought as well, and this is relevant for when you think about intensification, I think. So it makes a lot of changes if you use some fixed rate or you use this type of concept. What about the land use? Okay, so these are some examples from 35 farms in Spain, dairy farms, and the green one, the green color shows the land use from the farm point of view, and the yellow is showing the land use being happening somewhere else, mainly because all of the concentrates you are buying have been produced somewhere else. So that's some hectares somewhere. So you have two situations: some farms that have very low on-farm use, but then they have huge land use outside because they have a lot of concentrates in the proportion of the diet, and you have the opposite. And this is farms are not very far apart. So even though I have been using typologies, it's true that the variability amongst farms is greater really than the variability that you would expect from typologies sometimes. And moreover, we can use some land here or another, but it's very different if you use one land that cannot be used for anything other than the grassland production, or comparing to other land that can be a lot of things. So it's a lot of potential uses. It has more value. Especially we are talking about the areas that we are growing feed, and we could be growing food that can be directly fed to humans. So from this recent paper of animal food security, for example, they were using this type of information in global maps of grasslands use, and they were differentiated actually as well between grasslands. That they were differentiating the quality of this grassland, whether this grassland could be only used for grasslands, so marginal areas that can be only used for that, or there's nothing else, or grasslands that could be actually used also for crops. So they were kind of making that assessment. This is useful to know in the assessments. It's always difficult to know how certain this can be, this kind of information, to make this kind of evaluation of land use, but it's certainly interesting to take this land quality into account once we use about land use. Also, in connection, and we have already mentioned this before talking about these hectares, some of the feed that we are actually giving to the ruminants could be actually fed. Well, I don't know if directly, but very easily to humans. So what we did in one of the studies is trying to relate from these 17 farms that I mentioned before. Okay, we have every dot represents one of the dairy farms that we were evaluating in northern Spain. We were evaluating the carbon footprint. Okay, so this is representing the carbon footprint of each of the farms. And we tried to assess the ingredients that they were using in the diets of the farms, and we were separating those ingredients that we assessed could have been going directly to the human food chain, to those that were forages that couldn't have been eaten directly by humans. So we tried to establish whether there would be any relationship between the carbon footprint, and we found this relationship actually, that the diets that had these are the diets with less competition with human food, so had in this case a lower carbon footprint. So in this sense, what it was showing is that even though that these diets possibly are creating more methane from enteric fermentation, because some of these diets have typically ingredients such as soybean, quite a lot of amounts of soybeans that come from South America, and they have a big burden. Then it was showing that this would be really having an impact on the carbon footprint. So, trying to finish soon, and looking at these systems that I haven't talked about at all at this so far in Spain. What about the systems in the Mediterranean area? What are the problems that they are bringing with themselves? So these are the landless, very high yielding cattle systems. So we were actually working with this type of farms in one European project called OptiBarn, which was to deal with studying the heat stress on different farm systems in Europe and Israel. So these kind of farms in Spain were not, they would differ from the Israel ones, but they were not that different in essence. So there would be a lot of similarities. So just to remind you, very high yielding cattle and fully housed. So first thing of this, that we have to think into account even if we don't think about the heat stress, is that, and this we have found statistically, that, for example, the higher the yielding the cow has, the higher the productivity. For example, the more inseminations required to become pregnant. So it feels like there's a connection there, a clear connection with the fertility. It might be other reasons, but okay. And in terms of heat stress, what we try to model in this type of farms that would be suffering potentially on summer, especially in some times in spring and autumn from this heat stress, we were trying to evaluate what would be the effect on productivity and also on fertility. So incorporated some functions in the model. And so this is a comparison. So in red would be for 4 different consecutive lactations. Okay, this represents every lactation of this cow. The red one would be having the heat stress into consideration, and the blue one would be if we have just simulated the farm without heat stress. So the dotted here, the dots here, are representing the losses in productivity, possibly linked to some very hot periods in the year. And what we were also representing here was a loss in fertility, which was shown here as a delay to become pregnant again. So every lactation would take longer to become pregnant, longer and longer, and this would be also caused by some heat stress. Obviously, this type of systems wouldn't really go farther than 2 point something lactation. So this not really, that would be the pace that the cow would have about 4 lactations. It would be cooled much before generally. And generally would be possibly because failure of becoming pregnant. So we did some estimates for some Spanish areas of the potential loss in terms of economic losses for 3 different scenarios of climate change. So timelines as well, short term and mid term. So this is represented RCP 45, RCP 85. RCP 85 represents the information of the climate information that is more extreme from the models, that is coming more extreme. So that's why it's representing the, for these 2 different farms. Actually, the first farm here is represented for different months. It's a German farm and this is a Spanish farm. So we're doing that also for Germany, and just a proportion of the maximum potential productivity and the losses economically. This is it was showing, but that in some scenarios the losses were up to 50%. Obviously, from the scenarios that were very extreme. But I mean, this is just to exemplify that there are large potential losses if we don't adapt these farms. Yeah. Okay. So one other idea would be to increase the pressure on uplands. That's something I've heard that you want to do. You are investigating here. That's and it could have some. Could you just have more hectares or more intensification of these areas? So again, some work from here is showing that it's, you should be looking at N2O. It's maybe much lower, and this is someone from the audience here. Yes, showing you with the pointer. So it's much lower than 1%. So what about train methane? Well, has to be studied as well. So organic carbon, and also optimizing the carrying capacity will differ from optimizing the diversity that you can have in this kind of system. So this is interesting to be studied. Okay, I think I'm going to pass this one because I know that it's coming. I'm already getting a little bit people nervous. But it's here. It's about goats and about feeding byproducts to goats and how that can also reduce greenhouse gas emissions. So it's interesting. Okay, and apart from obviously strategies to intensify, if we look at the management, there are large possibilities as well. And I was choosing a couple of them, adjusting crude protein in the feed, in the diet. This is part of an existing project that I'm involved, which is led by university already. So we were trying to investigate using information from some long-term trials that have been doing both at Reading University and Aberystwyth as well, university, which is also involved. So having 2 different reductions of crude protein concentration in the diet. Our role was trying to model that at the farm level. So for the excretion, we modeled that there would be a reduction in excretion in these 2 scenarios of lower protein intake from concentrates. And if we look at the rest of the losses, so we would have that the lower protein, so all of the, this types are showing greater reductions in each of the axes, each of the variables that we are looking at. So we're looking at all of the losses that have to do with gases and leaching as well. So for both situations, there would be quite a lot of potentially improvements at the farm level. So obviously, another kind of last one would be trying to optimize fertilization, and this as well some study that we did some time ago. So we compare the typical fertilization that we had, and we try to optimize this fertilization depending on the weather conditions that we would have on a particular year, and we use the optimization routine within the Simsbury model. So by doing so, we actually change the patterns of fertilization, and we actually managed to reduce about 18% from the soil N2O and about 29% of the emissions coming from the manufacturing of the fertilizer, because we would be using much less fertilizer than it was actually thought about to produce the same amount of forage. So a total of 25 greenhouse gas reduction. So with that, I'm coming to the conclusions. So I will read them. So, okay, so one of the things that, as expected, sustainability is at least as important as intensification. Another issue would be how we define sustainability, which is still a big issue and we haven't talked about, but that's another seminar. So intensification through more efficient animals, even though it appears to have obviously shown some reductions in and improvement in sustainability, I mean, they don't necessarily lead to more sustainable systems, so it needs to be looked forward. Sustainable intensification must therefore address the whole system as a whole, farming system, and well, we should obviously look at land competition with different methods. I didn't include other methods that people at Bangor are using and probably are more useful, but to study this, so it's something that is already being studied, and I think it's important to include these non-human edible products for animals in the equation in terms of sustainability, especially with ruminants. We should not neglect social and economic dimensions. That's also obvious, and that's something I try to convey, the idea that choosing a methodology and assumption will have massive implications on the outputs, and especially on the relative outputs. So not just the absolute, but the relative comparison between systems. So this also intensification must be accompanied by changes in management that, all right, like I said before, increase use efficiency at the whole system level and not just at a component level. The stress for heat, but also for cold conditions, I didn't mention, but that can be also a great challenge in the future for more intensive farms. And as a final remark, even though I didn't talk about this, I think sustainable intensification can only address one aspect of global food systems, which is the supply side. But I think this would require a more integrated approach, which also takes into account the consumption as well, the food losses, the waste reduction side. And obviously the governance is a massive thing when we're talking about the areas that are still undernourishment. And with that, I just want to thank, and especially all of my Spanish collaborators. I didn't include the international ones, but there are some here as well. So, but these are my main team and some close collaborators in Spain. That's it. Thank you.